So my goal for today is to try and give you guys an overview of what's called the random algebraic method. I'll tell you lots of things, many of which are old and sort of already known, but now there are nicer sort of more enlightening ways of proving those things. I'll say at least the main results. The new results that I'll talk about are all based on joint work with Boris, who's at CMU, and Karthik, who has recently joined Rutgers. Okay. So this method has its, before I tell you what the method is, I should maybe give some attributions. So it has its origins in some work that Bukh did on geometric discrepancy theory, but at least the way in which it's become very applicable goes to some work that Boris did on constructing extremal graphs for the bipartite two-run problem. So this talk was officially titled Random Algebraic Varieties and Their Applications to Hardness Approximation. So the talk will be in two parts. So the first part will address the first half of the title. So I'll tell you something about random algebraic varieties. So here I'll mention one new result, but the goal will primarily be to give you new proofs of old results, nicer proofs, I'd like to think. So new methods, but old results. And the second half of the talk will be about telling you some applications, some new applications to hardness approximation. So here you will at least see some new applications, new results, but you will start seeing new results even in the first part. But if there's one thing that I want you to take away from this talk, it's that if I look at zero sets of random polynomials, these are random sets with a fair bit of independence that allows you to calculate a fair few things. But at the same time, they're rigid in ways that, binomial random sets are not. And so you can use these rigidity properties to do things that you can't with other sort of probabilistic models. So this is maybe the high level picture that I'd like you to go away with, if nothing else. So this is the goal for today. I'll presume zero familiarity with almost anything, so feel free to interrupt if anything's not clear. I will say one thing though, as a caveat right at the beginning, don't quiz me too hard on the computer science details of the second part of the talk. I'm not a computer scientist by training.
Well, you have a course with CS in the name. Right?
Yeah, so it's so this very much sort of happened in that Karthik came to Boris and me with some problems, and we realized that we could solve them, and it turned out they had some interesting applications. Okay, so that's the plan for today. So let's start. Let's start. So part one concerns the zero sets, random polynomials. Okay, so I'll start with almost a ridiculous toy question. Suppose I pick a polynomial in one variable with degree d, but I pick it uniformly at random. What can I say about the distribution of its roots? So the point that I'll make is this. The sort of algebraic varieties, they tend to snap into place. I like that word because it's sort of evocative of what's happening. So let's start with a toy question.
So just when you talk about a random polynomial, random out of what?
I'm going to tell you, yeah. Sorry, I was philosophizing, so when I do, yeah. No, you should sort of, yeah, hold me up to respectable mathematical standards, but I'll define what I'm talking about. So let's say that F is uniformly from polynomials in one variable of degree 2. So that's my notation. I might, on occasion, drop the Q because almost all the fields that we'll deal with for this talk will be finite fields. So if I write F, it'll almost always be FQ unless I say so otherwise. And the subscript G or less than equal to D or whatever, these are the obvious sort of degree restrictions. So the toy question is, what is the distribution of the number of roots, FQ roots of this polynomial? Okay, so I don't really want to know the exact probability distribution, though actually you can work it out. It's just a counting problem, I suppose. So here's the answer.
You expect one.
Say it again.
You expect one.
You expect one root on average, that's right.
It decays
Exactly, and then it decays. It's a sort of Poisson with mean one actually, with one sort of caveat. So we know that a polynomial of degree D can't have more than D roots unless it happens to be identically 0. So here's what the distribution looks like.
Sorry, I believe people on Zoom cannot see any board on the right.
What about the ones on the left?
No, also not.
Okay, maybe I should write smaller then. I'll split the boards. Okay, so here's the answer. The type problem. The distribution looks like this. So I have 0, 1, up to the degree D. And for example, the probability of having D roots, you can compute it asymptotically. Well, you can compute it exactly, but for Q large, this is like factorial. In fact, this looks like.
When you're talking about distribution, that's the distribution over FQ of what's the probability of that value to be an eigenvalue, or the distribution to have this amount of eigenvalues?
I'm talking about the distribution of the number of roots.
So roots.
It's just an integer valued, non-negative integer valued random variable. Number of roots. Yeah. Sorry. Yes. No, sorry. The number of things.
With multiplicity?
No, I'm talking about the number of distinct roots. Okay. Okay, so even if you don't want to know precisely what's happening, you can check that basically it's supported on 0 to D with some degree dependent maths at each point, but then it drops off sharply. This point it's a little over. The tail is negligible.
Yeah, it's not zero because you can have the zero.
It's not zero because you can trivially be zero, or you could be divisible by, you know, x to the p minus x or something. If the degree, but okay, I'm thinking if the degree is being fixed anyways.
Q is not a prime.
Yeah. No, Q is a prime, but anyways, the degree is small, so it could just be zero. If D was large, it might also be the case that you're divisible by a non-trivial polynomial that's just zero, right? Over finite field. Okay.
But then you should only have at most D root, right? If unless you're zero.
Oh, sorry. Yes, if D is large, regardless, there is no this part of the picture. So yeah. So if it's bigger than D, it's a zero polynomial. It has to be a zero polynomial. That has some chance of happening, but
are you thinking of D larger than Q?
I'm thinking of D fixed anyway, so this caveat was unnecessary. Okay, so think of D as fixed, like 100 and Q is going to infinity. So this is the picture. And the point is just that, you know, this rigidity that I sort of spoke about sort of manifests itself already. It looks like a Poisson random variable, but it's sort of chopped off at the end. Right.
Why did it say Poisson?
Well, this is a computation that I don't want to get into.
Okay. Yeah.
But it's an elementary computation. You just say, if I tell you a number of roots, you have to factor it like this, and okay.
Okay.
So the behavior of the tail changes sharply at this degree, right? And much of the talk will be concerned with higher dimensional, less trivial versions of this phenomenon. Okay, and there's a lot of power there, as you'll see. Okay. So, okay, this is a silly thing, but it's just to set the stage. Start with a motivating question. And let me tell you about Boris's original sort of work that a lot of this comes from. I'll give you a different proof of Boris's original construction. Allow me to advertise the main new thing that we proved. So here's the motivating question that a lot of this is tied to. And this is the Kollar theorem. I hope I'm not missing any accents on. And the question is this: how many edges can an n-vertex graph G have if it doesn't contain any copies of a fixed complete bipartite?
The graph itself is not complete bipartite, but you lose or something.
It loses nothing,
Yeah, it loses one.
a factor of 2, but if we want to keep it clean, we can make G bipartite. No copies of. Let me even make it clean. N, N bipartite. But no copies of DST.
Zarankiewicz question. It's their paper, but it's a Zarankiewicz.
Exactly. Zarankiewicz is the ordered version, I suppose. Is the sort of matrix formulation, but yeah. But for this particular question, it's all the same. And of course, a lot is known. It's called the Curry-Schoch-Stern problem because, of course, they proved what remains more or less the best upper bound. It's a simple double counting argument that I won't show you, but if you haven't seen it, I urge you to go see it. Double counting plus some convexity shows you that the answer is big O of n to the 2 minus 1 over s. Let's say that s is at least at most t. You get it with t as well, but you should write down the better bound. But lower bounds, on the other hand, are not readily available. We don't know very good constructions in general. So what do we know in terms of lower bounds? Well, in some sense, not much, because in some ways, the most interesting case is when s equals t. In this case, we have no idea except for some sporadic small values, where some projective plane type constructions tell you something. But in general, little is known. What we do know is that when t is much bigger than s, I'm not going to quantify it, but if you need a number in mind, think of s to the s. We do have matching lower bounds. And I should mention a few different names.
I'm confused about this upper bound. So
Say that again, sorry.
I'm confused about these parameters here.
Okay.
So like when s is 1, then the number of edges is number than tn. So should there be?
S is, you should start from S is 2.
Yeah. Maybe I should.
Forbid us, a cycle of length 4.
Yeah.
Right, and then it should be n to the 3 halves.
Yeah.
And it's
And s equals t equals 2.
Yeah, but why is t on the right? So you're saying?
It's a condition.
I'm saying when s is at most t.
Oh my gosh. So sorry.
I mean, you can also write down the bound with t, but you might as well write down the slightly better.
Sorry.
That's okay. Yes, feel free to ask anything that's unclear. So it's been a fair bit of work into specifying precisely how big t needs to be to get matching bounds. So I'll mention a few different names who've all been involved with this sort of thing. Noga, Kanosh, Ronyai, Tibor, potentially other names that I'm missing out
The
on.
original paper is Kollar, Ronyai, and Szabo, and
Yeah,
then
this is
the improvements. Yeah.
That's right, yeah. Those were the 3 people who originally found this construction, an algebraic construction once again, and potentially other names that are not on my list, but most recently, Boris found a way of constructing these graphs. And what's different from the other construction in Boris's construction is that the previous constructions are explicit in that they're algebraic, but you write down what the algebraic definition of these graphs are. Whereas Boris's construction mixes probability and algebra. And this backed up a fair bit of interest and since proved useful in studying this problem, a few different things that have now yielded to this method. And let me motivate why such a method works, or why you should even think about using such a method. So let's try the obvious sort of construction.
Why do you say little's known? When it matches?
Because
I'm hiding a lot of things here.
Oh, so.
Yeah. So
if
they're
you want,
very imbalanced.
okay, take K44, we have no idea what the
So t literally is like, has to be at least 2.
So the current record is actually Exponentialness, which is in a preprint due to Boris. He's really refined the methods that I'll be talking about today. But I mean, unless you really want to work on this problem, it's not a paper that I'd recommend reading because it has a fair bit of heavy machinery going on inside. And it's unlikely that these techniques will let you settle the S equals T problem. That's my feeling. Boris, from what I know, is maybe even skeptical that n to the 2 minus 1 over S is tight for S equals T in general. But anyways, I'm not claiming that this method will settle this problem. This much I'm reasonably confident of. famous last words, etc. Okay. Let's look at a random graph. So a bipartite random graph. So let's try G, let's say NNP. So two blobs of size n, each edge in between I'll put in the probability P. And I'll pick P to be what I want to get these many edges. So let's say P is n to the minus 1 over s. Then the expected number of edges is okay. It's what we want it to be. Which is n to the 2 minus 1 over s. So let's now try and count these bi-cliques. So let's fix some set U of size s on the left. Let's call these things A and B, I suppose. Fix U inside A, size s. Let me look at its common neighborhood. So bi-clique just means that everything in U, these vertices, they have a common neighborhood of size t. We'll consider, well, generally, consider the distribution of the size of this common neighborhood. So what is this distribution?
Yeah, but no, it is non-standard notation. These are the common neighbors.
Sorry, yes. So the set of common neighbors of everything. So a vertex goes in the set if it's joined to everything. What can I say about the distribution of this? One can say what is exactly, it's binomial. So this is.
Oh, roughly.
Say it again.
Binomial n p to the s, which is roughly Poisson.
That's right. And that is binomial n 1 over n by my choice of p. That's essentially Poisson 1. Right? And so this distribution looks like this. So I'm interested in KSTs, remember? So it goes from 0 up to t, has like a 1 over t factorial chance of having t neighbors, similar chance of having fewer neighbors, but annoyingly, there's some chance that I'll have more neighbors as well. And so if you use these bounds to compute
the bottom board ourselves.
Say it again. Yes, sorry. So if we do a union bound, I'm not going to write down the details, but for the number of KSTs, we see that becomes tiny when, unfortunately, not when t is a large function of s, but rather when t is sufficiently sort of slowly growing in n. Let's say 10s log n or whatever.
Does the lowest local lemma help with something?
Not as far as I'm aware of.
Oh, it also doesn't help with the usual Ramsey number. May affect a tiny constant, but
Well, for what it's worth, this is tight. If you replace 10s by 0.1s, a second moment calculation shows you that actually you will find these. Okay, that's unfortunate. So what do you need? You need 1 over t factorial to kill n choose s. So that's where the numbers are coming. Okay. So what's the problem? The problem is this Poisson tail over here. If we could somehow arrange for the size of this neighborhood to have a chopped off sort of tail, we'd be better off. So currently, I look at the size of the neighborhood, it's sort of supported on, well, it's supported on the natural numbers, that's the problem. There's a long smooth tail. And hopefully, the way I've sort of arranged things, the toy problem is now suggested. What we'd like is something like in the toy problem, where there's some support here from 0 to t. But then you want to chop all this up. You want it to be more sort of rigid. Okay. So before I tell you how to ensure that we can do this, let's switch tacks. Let me talk about Bézout's theorem. So keep this question in mind. This is our motivation for the first part of the talk. Let me maybe write it down informally. Caveat. So let me work over an algebraically closed field. This is important. Closed, algebraically closed. Field and K polynomials and K. Okay. And let's consider the variety that they cut out, i.e. the set of their common zeros.
Important for you to have the same number of variables and equations, so you get a finite number of solutions.
That's right.
Yeah.
Or generically, you'll get a finite number of solutions. Then, I won't go into this assumption in any detail, but assuming that the Fi is a generic or a general position, then almost certainly this variety is zero-dimensional, i.e. it's just a finite set. And again, almost surely, under this genericity hypothesis, the size of W is the product of the degrees. Okay. So it's a perfectly determined system. It's not overdetermined, it's not underdetermined, and that's important. So here's the main sort of thing that we proved, Boris, Karthik, and I. We proved a probabilistic version of Bézout's theorem for a finite field. So let me tell you what it says. So this is from our paper. Instead of now looking at generic polynomials, you sample polynomials randomly. So let so for 1 up to k, take Fi from the polynomials of degree di uniformly and independent of the other. And let's write Z. Shared zeros in FQ to the K, not in the closure. Number of distinct zeros. And well, what do we expect going from the one-dimensional case and from the zoo? We expect the Z to be supported on 0 to the product of the degrees, and then to be very unlikely to have any larger value, because more or less that would, the only way that can arise is from a common factor, more or less, something of that nature. Then writing D for the product of the degrees, capital D. As Q is large. So this is, you'll see, a sort of sticking point for almost everything I'll talk about. To prove these things, unfortunately, you do need the size of the field to be much larger than the degrees of things that you're interested in. And I'll tell you where this comes from in a second. The probability that Z, for example, equals T is exactly what you think it is. Or D factorial, more or less. Whereas the probability that it's any bigger is now tiny, or small, Q to the smallest of these degrees. I'm not entirely sure this is tight. I haven't spent a huge amount of time thinking about it. Applications, this is plenty. This is tight. So a couple of remarks about this. Let's take the zoom.
You need the Q to go to infinity for this to be correct, or for killing the union bound for any n?
I need Q to be large even for that, for these statements, really.
Without the application.
Yeah, there are error terms in some of, I'll tell you in a second why.
Yeah.
For applications, we need it as well, but at least in the applications that we found, this is a minor sticking point, but I can certainly imagine applications where it would be nice to not have this restriction. You might
So
even be.
no e to the minus 1 factor?
Say that again, sorry?
So there's no e to the minus 1 factor?
No, what factor, sorry?
1 plus the little 1 factor.
Oh, what about it?
Like if it were a Poisson distribution, there would be a 1 over e factor.
Would there? It's exactly D. Good question. So yeah, actually, maybe there is no Poissonness. Maybe that doesn't exist. Yeah, sort of Poisson-like, but this is what comes out with the argument. It's a good point. I didn't think about this. In fact, I might even be lying. I think we only wrote down the upper bound. That's at most 1 plus little 1 over d factorial. And I believe the proof gives 1 over d factorial, but I didn't check all the details. So if you want to use it, just, yeah, sorry, the proof gives a lower bound, sorry, for the z equals t. So actually, this might be wrong, what I've written. I somehow blindly assume that a second heuristic calculation is true, but let me be precise. This is certainly true. So there is support up to, well, what you expect, and then it sort of drops off. Thank you. So some remarks. about this. Number 2. First, the 1 over d factorial type bound is the best you can hope for. And it's possible that the answer is e over d factorial. I don't make claims at the board, but the shape of the bound is the right down. Jordan Ellenberg, he showed us a heuristic monodromy calculation that justifies this and can be made rigorous if you have the energy. We'll say here it's heuristic. We had other heuristic calculations also justifying this, so I believe this. And if you put a gun up to my head, I'll prove it. But as I said, for applications, you only ever need that lower bound. The second one, which is a point that Avi sort of brought up tangentially, overdetermined or underdetermined systems are easy. These you don't have to worry about. So really, the beef is in these systems that are at the correct number of polynomials and the correct number of variables. So if you have fewer than k polynomials and k variables that you pick randomly, then you can show that the number of roots is with high probability, at least, let's say, q, some constants. And this is not hard, this is just a moment argument. You can compute large finite moments of the number of roots. And for overdetermined systems, well, even if you have a perfectly determined system, it's got finitely many roots with high probability. So the chance of the next polynomial in your system vanishing anywhere is just minuscule.
Good for intuition to consider all the degrees being 1, and then at least you see why you get 0.2 in linear systems. If one is missing, then you get.
Yeah, exactly. Okay, so this is the main sort of thing that we prove. I'll maybe just say, without going into the details, what's the main sort of input from algebraic geometry? All of these things rely on what are called the Lang-Weyl bounds. So if you know what these are, then you know what I'm talking about. And if not, I don't want to expand because I don't have a huge amount of time left.
The number of roots of polynomial, low degree polynomials over finite fields.
Yeah.
This is what you need.
Yeah, they give you more fine-grained information.
Oh, of course, yeah.
Yeah, but yeah, that's precisely what they do. Yeah, yeah. And annoyingly, we do need the fine-grained bits of information to prove at least this bound. This one has a cheaper proof. Okay. Though for all I know, if you just wanted some function of d there that wasn't d factorial, maybe we'll get away with less. Okay. All right, good. So why is this helpful? Let me sketch a construction of extremal graphs for this covariant problem, and then move on to part 2. So here's A, so n is just going to be q to the s. I'm going to pick for each point in A a random polynomial. And S variables of degree, let's say, S squared plus 1. Okay, the details are not hugely important. B is just going to be F between S. I join some F to some X if F of X is 0. Right. And I'm not going to even give you the details because you should be able to work it out from probabilistic Bazoo. The chance of this collection of a collection of points having lots of roots is just really, really small. It's like q to the minus s squared plus 1. And that'll let you do union bounds over all sets of size s.
But this would give something worse than the explicit construction of Kollar, Ronyai.
Sure, in terms of the dependence.
They get S factorial.
Sure.
This seems worse.
Yeah, this is worse. But my only reason for showing this particular construction was that it's easy. There's no claim to sort of anything new. It's just this probabilistic version of Bazoo is new. This, not claiming any originality, just reproves things.
The basic method here is that you can define graph by having points on one side, polynomials on the other.
Yeah.
The number of roots relates to that.
Okay. So let's move to
We're using something much weaker than the first conclusion that, the lower bound. Of
correct. We only need the second bound for this. But the reason I wrote it down in full generality was that it proves useful in the second part of the talk. Will admittedly be shorter. Part 2, let's talk about some applications to complexity. So first, it's not surprising that this has applications. So for example, if you know some of the older literature, you know that non-graphs, i.e. the original sort of KST graphs, we use to prove super polynomial lower bounds on the size of monotone span programs.
It's in the left.
Non-graph is a graph like this.
It's a graph like this. It's
It's
deterministic.
this explicit construction of Kollar, Ronyai.
That's right. So I'll tell you about two things that we were able to prove using probabilistic Bazoo about set intersection. Actually, maybe I'll just not waste space. Maybe just write down the set intersection. So the problem I'm sure you all know about. So you're given n subsets of 1 up to n. Let's say k set intersection, and you want think of k as a parameter, and you want to find k sets whose intersection is as large as possible. And the trivial algorithm is to just take all possible subsets of size k and try them. And the results I'll sort of describe more or less say that that is the only thing you can do under sort of various hypotheses.
Want it exactly, not approximate.
Say it again.
You want the maximum exactly, not approximate.
As I've stated it, but I'll also talk about approximation. So the first thing is that not much was known about hardness for this until what I'm told is a very serious paper of Lin, I think around late 2010s, who showed that under the standard sort of hypothesis that there's no polynomial time approximation algorithm. Any pair of computable functions, f and t, but the polynomial has to be independent too.
Yeah, I'm not sure that everybody is familiar with the assumption. Like,
to be honest, I'm not.
Okay.
Yeah, I'm not familiar with it either. I just know that it's the standard hypothesis in.
Yeah, it's parameterized complexity assumption analogous to P versus NP for problems in which there is an extra parameter like K here, and you are shooting for an algorithm that will run in time polynomial in N and arbitrary dependence on K. So in this problem, it seems like you need N to the K, so it doesn't have this property. There are many other problems like this. So yeah, this is a typical type of result under this assumption. You cannot have an algorithm of this type. But you want what kind of approximation factor or some?
It doesn't matter.
Yeah, okay. So it depends on the.
Just depends on K, but you can't do it.
Yeah.
But this is a hard proof from what I understand. And the reason it's hard is because Lin wanted what are called threshold graphs. I won't bother to describe them in detail. If these things existed, Lin's proof is, half a page, but they didn't exist at the time when he was thinking about these things, and he had to work quite hard to prove this theorem. Well, it turns out the construction I've showed you, in fact, proves that these graphs exist. I haven't told you precisely what they are. You basically need to show that not only do you not have these K sets that have small neighborhoods, but that K-1 sets on the left have large neighborhoods. Non-graphs, annoyingly, you can't prove this, but one advantage of the probabilistic sort of construction is that you can prove it. So this follows. I mean, it's sort of cheating to say this follows from the previous construction, and I haven't told you what they are, but in the interest of time, I'll say. Okay, so that's one.
So this is just plugging in just what's written on the top border, the same construction, and just using the situation where it's underdetermined. You have many rules.
Exactly.
Otherwise, precisely.
Exactly. So it's cheap.
Say again about F and T. I didn't catch what you said about the FK and the T, the two functions.
These are just any computable functions of K. So think of K as your parameter. You can do whatever you want with respect to that. Okay. Arguably, I mean, okay, this gives you a simpler argument, but this is not news. One sort of interesting general thing that we can do, sort of come up with a general recipe to reverse what's called the color coding technique. So this, the general method of Alon Yusser and Zwick, and it helps you transform an uncolored problem to its colored variant in a computationally sort of lossless way.
Let's say one more sentence.
Please.
This set intersection problem is a problem which does not have a flexible fixed parameter algorithm. That's what this does. Is Another problem which does, and it's sort of surprising that it does because it looks the same, and the proof is using this color coding paper, and the problem is very simple. Does there exist a path of length k in a given directed graph? You can again do it in n to the k time, but using color coding, which is really beautiful, you can do it in 2 to the k times n, which is a fixed parameter. I don't know what results coding is, but I know.
Yeah, I don't have the time to really tell you what this is, but it's this lovely technique to go from quote unquote uncolored problems to colored problems in a lossless way, in a computationally lossless way. And it will be handy to have some sort of recipe that's similar that allows you to go backwards. As Avi says, lots of interesting things have been proved using this technique. Something that my co-author Karthik had done before we were working on this problem, and in fact, this is where we started working on this problem, was that he'd shown with the co-authors, write down the names. Karthik, my co-author. Okay, I think. We sort of said that yes, there's a sort of general way to go in the other direction if, I should say general in that in many cases that they were thinking about.
Maybe I'll say another sentence, Bhargav, if it's okay, because you're talking about going in the reverse of this direction, but nothing was said about it.
Going forwards, yeah.
Just continuing what
Please,
I said. You look for a path of length k, and you don't want to try all of them. You say, well, let me randomly color the vertices by k colors. And then if there was a k path, then there will be a, with some probability, at least depending on k, that this path will have distinct colors. And now let me search only for paths in which all vertices have distinct. And this, given the colors, can be done by dynamic programming, and you don't. That's not the only thing is having the probability right that it will happen, but that saves you from
do a k factorial to
the k factor. So I still don't know what you mean going in reverse.
So, unfortunately, I don't have the time to tell you precisely what I mean, but
is the type of statement something like saying that if the colored problem is hard, then also the original?
Exactly.
Okay.
Yeah, that's what I mean. More generally, there's some lossless way showing, more or less order one equivalence or something of the two sort of problems in terms of their complexity. Where the order one hides the parameter. In instances, if certain things called panchromatic graphs exist. So in the same way that Lin's theorem would have been easy if these threshold graphs existed at the time, these guys showed that there's a reasonably general method to reverse this idea if you can construct what are called panchromatic graphs. Well, maybe quickly say a word about what these are. And by seeing them, you'll sort of get some feeling for why they help. we'd somehow like to take a colored problem and embed it in such a way that once you've solved the uncolored problem, you've actually solved the colored problem. And so this is what the graphs will look like. So the bipartite graphs again. Left-hand side is split into k pieces, each of size n. The right-hand side consists of one piece, size n. So here's the property that you want to have. You want to say that if I pick k vertices, one from each color, these guys have really large common neighborhoods. I'm sorry, I'm not telling you why this is the thing you want, but turns out this is the gadget that you need to make the idea work. There is any k set that, let's say, repeats a point, it must have small common neighborhoods. So think of k as fixed. Large and small are just specified in terms of k, but n, you need these to exist along a suitably dense set of values n for their sort of construction to work. Okay, and the final point is that these probabilistic algebraic arguments, they allow you to prove that these exist. And I can even say one word about how you construct them. It's quite easy. Once you have the idea, I won't write it, just saying yes, they exist. The idea is this: with each color, you associate a large random polynomial of large degree. And then for each vertex, you then pick its own sort of random polynomial of small degree. Okay, and you associate a point with the sum of that big polynomial and the small polynomial. So then if you look at the roots of a system that spans all the colors, this is just distributed like the number of roots of k polynomials of large degree. Right? The addition of this small random polynomial changes nothing. Whereas if you repeat a color, well, you subtract off those polynomials, then you've changed the degree of the system that you're working with, and we have pretty good control as to what the number of roots looks like. So that's where the construction comes from. Okay. So I'll start by mentioning some consequences for this k-set intersection problem. The under strong hypotheses, admittedly, ETH can't do any approximation in n to the omega of k time. So I think it was previously known that under the same hypothesis, you can't do n to the omega of square root k or something, but this is essentially less possible. And if you strengthen the hypotheses, you get with the strong exponential time hypotheses, you essentially need n to the k time for any f of k factor approximation. So those are some nice things that come out of these constructions. Okay, I'll stop there.
All right.
Take a rest.
Questions? So you mentioned that Boris has a way to reduce the factorial dependence to exponential in the Zarankiewicz.
Yeah.
So that seems pretty amazing because it's
This is really impressive.
Go beyond anything like the Bezout type argument.
Yeah, so it still uses random polynomials. They just come from very different spaces. Yeah. I haven't digested all of it myself.
Amazing. Okay.
Yeah, this is very impressive. This is the current record, and it's very technically impressive.
More questions? Okay, Thanks.